All that lovely speech I didn't record. Oh well, but we did here. And that's far, far better quality than this.
Hi guys, my name is Dimitrije and today I will be presenting my thesis, which is called Two-Wheel Self-Balancing Robot. And the motivation for this project is because past summer I had an internship in which I learned a few things about hardware and about microcontrollers. So I decided to kind of expand on that knowledge, and because one of my interests after school is to get into robotics. So with that being said, let's start. So first I got a brief introduction about what is this. It is an Arduino controlled two-wheel robot which balances itself. It does this by using different parts of hardware such as microcontroller, gyroscope and accelerometer sensor, and motor driver. It also uses a PID controller to control the robot, and PID is actually a short abbreviation for proportional integral derivative. Okay. So first I got just a list of hardware parts that I used for this project. First is 3D printed chassis. I used, my microcontroller was Arduino Mega 2560. I also used a small breadboard. I used MPU 6050 as my sensor. I used L9110 motor driver, 2-gear DC motors, and 2 AA batteries. These are the parts that my first demo was composed of last semester. And here we have Arduino Nano. We have 9110 motor driver, MPU 9265, and 2 DC motors. And for my final version of my parts changed up a little bit because I'll talk about that in a second. So as you can see here, instead of Nano, I have Arduino Mega 2560. We have the same motor driver. My sensor also changed. It is not 9265, it's MPU 6050. And my motors are the same. And with that being said, I'm going to go over the differences between the parts that I used in my first demo and the parts that I used for my final version. So first, Arduino Nano was much smaller than Arduino Mega, and I needed a lot of pins. I wasn't sure how many pins I'm going to need for this project, so I decided to upgrade and get something with more pins. And so as you can see, it's much smaller. It only has 14 digital input-output pins. It has only 8 analog input pins, and also has much less processing power and memory. However, Arduino Mega is much bigger. It has 54 digital input-output pins, and it has 16 analog. And along with that, it also has much more processing power and memory. So if your code does get complex, you're still able to upload it and run it with no problem. The next thing is the motor driver that I wanted to use versus the motor driver I'm using right now, and I'll talk about how and why I wasn't able to use the motor driver that I wanted to. So my original idea was to use this L298 motor driver, and compared to the motor driver I'm using right now, it can control the speed of my wheels, and it can also control the direction. And speed is controlled with PWM signals, and PWM signals are pulse width modulation signals. It can also provide much more power to my motors, and it also requires more power. So that's that. So this is a little more details about the motor driver that I wanted to use. As you can see, it runs on voltage between 5 and 35 volts, which is kind of high, with peak current up to 2 amperes. It also has voltage drop of 2 volts, so that means if your power supply for your motor driver is 9 volts, that means your motors are going to get 2 volts less, so they're going to get 7 volts. My motors work well between 4 to 7 volts, and they can get good speed at about 6 volts. So next we have difference between my sensors. So this is 9265 is the sensor I used in my first demo, and this MPU 650 is the one I used for my final version. So the difference between these two sensors is that MPU9265 has it's a 9-axis sensor, which means you will get 3 values for accelerometer in XYZ, 3 values for gyroscope, and 3 values for a magnetometer. And my other sensor is only 6-axis sensor because it provides 3 values for accelerometer and gyroscope. So there is no magnetometer. So what is this sensor and how does it work? So as I already said, it's a 6-axis sensor, and it can help you get the position of the object it is attached to in 3D space, so XYZ values. Also, I felt like it's important to know that these sensors are really cheap and they have a lot of drift and error. So if a sensor was to have only accelerometer or gyroscope, the values would be like really unstable. But luckily enough, there is sensors in which accelerometer and gyroscope are embedded at the same chip, and you're able to use accelerometer values and gyroscope values to cancel their noise and get your values to be much more stable. So that's that. So here I have a screenshot of the values when I used my first sensor, which is a 9-axis sensor. And as you can see, the values are really, really unstable. These are accelerometer values, and we have gyroscope values over there. As you can see, they're jumping by 100 up and down, sometimes 200, 300. And that was really inconvenient for my project because I really needed my values to be really stable. So I was able to get around that by getting this new sensor, MPU65. And with that, I was able to get yaw, pitch, and roll values. And if any of you guys don't know, I just have a little picture just so you can get the idea of what those values are. And also these values are in degrees. So by not having magnetometer, I was able to get my gyroscope and accelerometer values much more stable. And as you can see, they're really, really stable. All 3 values are pretty much not moving. Okay, there we go. So by getting this part done, I was able to do something, in my opinion, it was pretty cool to learn. I was able to visualize my sensor data as a 3D model, which I will show you guys at the end. And I did this by using software called Processing and open source library called Toxic Libs. And Processing is a software similar to Arduino software, except it has a little more functionality, and it can visualize data in a 3D model or 2D. The next thing I use is called Toxic Libs. And Toxic Libs is an open source library, and it is used along with this processing software for computational design tasks. And by combining these two things, I was able to create a 3D model which corresponds to the movement of my robot. The next thing I use is called PID controller, and PID controller is based on my sensor values, and it gives you the ability to feed the motors a different speed based on how tilted the robot is. So let's say the robot tilts just a little bit, the motors are supposed to go really slow, and if it's tilted a lot, then it's supposed to be going faster. So based on the values that I was able to get, yaw, pitch, and roll values, I was able to produce a PMW output to the motors based on how tilted the robot is. So power supply. So for my power supply, I had a lot of problems, and for me that was one of the biggest challenges in this project. I'm only using 2 AA batteries to power my sensor, and my Arduino and my motor driver are powered by my laptop. And the reason for that is since I wasn't able to get my 9-volt battery to work at all, I wasn't able to use the motor driver that I wanted to use because it didn't have enough external power, and I was required to stick with my old motor driver. And I'll show you how that affected the end result. So I have a picture, also have a picture of my connections. So as you can see at the top, I have my Arduino Mega. I have in the middle a breadboard and a sensor attached to it. I also have my motor driver over here, power supply, and 2 motors. And I have the connections just thrown out. I was able to use this by cool software called Fritzing, and you can just drag and move parts around. You can create connections, which is pretty cool. Next thing is chassis. In the beginning, this postponed a lot of my progress because I couldn't find a way to build my chassis. And the suggestion I got was to use a 3D printer. And I was able to, so using Tinkercad, which is a web app, I was able to create a 3D model, save it as an STL file. And that, for the guys that don't know what STL file is, those are the files that are used by 3D printers, and by creating an STL file, I was able to print out my my chassis. Here I have a picture of my chassis. That's an STL file, and this is how my assembled robot looks like. So at the very top, I have my microcontroller. Below that, I have my sensor attached to a breadboard. And on the bottom level, I have my motor driver and my AA batteries. And of course, on the side, I have motors and my wheels. Time for demo. So first, I'm going to show you guys how my 3D modeling works. Just give it a second. It kind of takes a few seconds to run. Okay. And it also needs a few seconds for values to really stabilize. So we'll give it a few seconds. So, as you can see, when I tilt my robot like this, the plane corresponds to the movement. It also spins in every direction. And it's pretty responsive too. So that's that. The next thing I'm going to show you the actual balancing of my robot. So the actual balancing of the robot is not great because I was required to stick with my old motor driver, and I wasn't able. This old motor driver is not able to produce PMW signals, so my motors are always spinning at the same speed. And as soon as my sensor senses a little tilt, my motors are going to go full speed. So the balancing itself does not work, is not perfect. But so as you can see, this is the robot in the center position. When I tilt it this way, the wheels correspond. Also this way. So let's see how it works. As you can see, it's not perfect, but just because my motors are not able to get different torque, the balancing itself is not perfect, but that's the closest I got so far. So that's for that. So now I have challenges and workarounds, and I had a lot of challenges throughout this project because, as Professor Perry already said, we don't have classes on hardware, so I had to do a lot of research by myself, a lot of trial and error, a lot of connecting parts and making sure their connections are good. So first, my chassis made things a little bit more complicated in the beginning because I had to ask a lot of people if we have 3D printers at this school and how to use it, who do I contact, what file should I provide them with. So that kind of made things a little harder for me. Of course, I had issues with my motor driver because I wasn't able to get my external source of power to work. And I also had issues with my sensor. As I already said, my previous sensor had that magnetometer in it, and that made my accelerometer and gyroscope values to drift and have a lot of error. So I was able to get around that by getting a new sensor. So kind of for the end, I wanted to kind of reflect on this project and just see what I learned from it. And I think I learned a lot because this project used both hardware and software. And I just think I grew as a person, and more importantly, I grew as a programmer. And yeah, it was fun doing this project. And yeah, that's it. Do you guys have any questions for me? Yeah.
So you've got the virtual interpretation, showing all the yaw and the roll and stuff like that. Do you use that to, like with change in planar slope and stuff, to determine what's going on and how to counter-correct for it?
Yeah. So more specifically, yaw value is used to detect, because yaw value is literally detected by moving the robot forwards and backwards. But unfortunately, my PID controller is not as effective because I always get the same speed for my wheels, so it is not as effective. But yeah.
How easy would it be to swap in the proper motor controller and have it work as intended?
Honestly, I think it would probably take me like an hour or two. So the only thing I needed to get is a 9-volt battery and a connector, and make sure I can power all my parts with it. But for some reason, I wasn't able to get all my parts to get run on 9-volt battery. I was only able to get my Arduino to work on it, but my motor wasn't responding. So. Yep.
So seeing this makes me appreciate I'm sure everyone's seen the videos of, I think it's Boston Dynamics.
Yeah.
The 2 and 4 legged robots that push over.
Yeah.
But you mentioned some, I think it was hardware simulation software that you used to kind of design how the components work together. What did that, how did that help you, or what benefit did that using that software do?
So, midway through my project, I kind of realized that it's a lot of like hardware based, and I really don't know what specifically I want to do after school. So I thought maybe combining hardware and software would like open a lot of doors for me, and hopefully make me decide what field I want to go into. So yeah.
So that helped you design, or did it?
It helped me. Yeah, it kind of helped me design because I was able to actually see my sensor values visualized. So I was able to see how my robot will move with those values.
How hard would you say it would be to change from a ground vehicle to, like, say, a drone, a flying drone?
A flying drone? Well, I'm not sure about flying drones, but I'm pretty sure it would require more parts, and these parts are cheap.
Well,
so,
software-wise, specifically.
Software-wise, well, it would probably be a little harder, but I'm not really sure. This is the first robot I built, so I'm not really sure how would that affect the size, and the size of the robot. Yep.
Was it just for more pins that you switched to the Mega Arduino?
More processing power, because I wasn't sure if my Arduino Nano is going to have enough processing power to do all those calculations as fast as I want them to. So I just switched just to make sure, Yeah.
So then, one more question. We're looking back. Do you think it could handle it, or do you think it was a good decision?
Honestly, I think it could, I haven't tried it, but I think it could. I had enough pins on my Nano, but it's the other thing is if I decide to build upon this project in the future, I'm able to use. There's a lot more pins, and you're able to add more parts to it. It's scalable, pretty much. Yeah. Yep.
So initially, you were going to have two separate motors that could turn at different speeds, possibly in different directions.
Yeah, different speeds was the key for balancing, but since my motor driver cannot do that, I wasn't able to have my balancing as effective as I wanted it to.
Sure. So then both motors go in the same direction, the same speed.
Yeah, yeah.
It's pretty rough.
So forward and backwards, yeah. Thank you, guys.
Well done.